We live in a universe where nothing lasts forever. Mountains erode, stars burn out, even atoms eventually decay. You accept this as obvious. Everything ends, everything transforms. Impermanence is nature's rule, except you've been told. For black holes are the exception, the one thing that doesn't end. Cosmic prisons so absolute that once something crosses the event horizon, it's gone forever. Not just invisible, actually gone. Matter, energy, information, trapped for all eternity behind a gravitational barrier nothing can breach, not even light. Everyone knows this. It's repeated in documentaries, taught in classrooms, stated with scientific certainty. Here's the uncomfortable truth. Everyone is wrong. Black holes evaporate. They emit particles. They shrink. They have temperature, actual, measurable temperature. And given enough time, they disappear entirely in explosions of radiation. The universe doesn't create permanent prisons, after all. It creates temporary bonds, however long-lasting. This isn't a minor correction or a semantic quibble. This is quantum mechanics defeating the most extreme gravitational confinement imaginable. The implications are extraordinary. If black holes aren't eternal, then the universe preserves information even in its most extreme conditions. Then permanence is nowhere to be found in nature. Then the cosmos maintains consistency in ways we're only beginning to understand. What we thought we knew about the universe's most dramatic objects was incomplete. The reality is stranger, more elegant, and more comprehensible than we imagined. As we shall see, nothing, not even nothing escaping, is quite what it seems. We find ourselves obsessed with black holes, and for good reason. They are the universe's most dramatic objects, regions where gravity becomes so intense that not even light can escape. The very name conjures images of cosmic drains, swirling vortices that devour everything within reach and hold it prisoner for eternity. This is the story we tell ourselves. It has a certain poetic finality to it. But here's the strange thing. This story is fundamentally wrong. The phrase, "nothing escapes a black hole," has become physics gospel. You've heard it in documentaries, read it in textbooks, encountered it in casual conversations about space. It's repeated so often, it sounds like a law of nature, as fundamental as gravity itself or the speed of light. Scientists state it with confidence. Science communicators present it as settled fact. Even physics students memorize it for examinations. This is the most widespread misconception in all of popular physics. Black holes are not eternal prisons. They are not unchanging monuments to gravitational tyranny. They do not last forever, accumulating the universe's secrets behind impenetrable barriers. They are temporary structures, dynamic, evolving objects that slowly radiate energy, shrink, and eventually disappear entirely in explosions of high-energy particles. The defining characteristic everyone knows about black holes is false. Now, before you dismiss this as sensationalism or misinterpretation, understand what we're actually saying. The misconception isn't a simple error or a matter of semantics. It's a classical prediction that quantum mechanics contradicts. Einstein's general relativity, a theory of extraordinary precision and elegance, predicts event horizons from which nothing escapes. The mathematics is rigorous. The observations confirm it. And yet the complete picture requires quantum mechanics, which reveals something Einstein's equations alone cannot. Black holes emit particles and slowly evaporate. This matters profoundly. If black holes truly lasted forever and destroyed information permanently, the universe would be engaged in systematic violation of its own rules. Quantum mechanics is reversible and unitary. Information cannot simply disappear. The laws governing atomic behavior, chemical reactions, the very structure of matter itself, demand that the universe preserve its complete quantum state through time. You can, in principle, calculate backwards from any present moment to reconstruct the past. This isn't philosophy. This is how quantum mechanics functions at its most fundamental level. But permanent black holes would destroy this reversibility. Every star that collapses, every particle that crosses an event horizon, would take its quantum information into oblivion. The past would become genuinely unknowable, not because we lack the computing power to reconstruct it, but because the data would have been erased from reality itself. The universe would become fundamentally ambiguous. Consider what this means. If information can be destroyed, then identical present states could arise from different histories. The laws of physics would have escape clauses. Different rules would apply in different places. Determinism inside black holes, reversibility everywhere else. This is intellectually unsatisfying, certainly. But more than that, it's physically problematic. It suggests the universe has different physics depending on location, that the elegant mathematical structures governing nature have special exemptions for extreme gravitational conditions. Nature doesn't operate this way. Einstein himself never believed in black holes despite his equations predicting them. He found the whole idea disturbing enough to spend considerable effort trying to prove they couldn't exist. His discomfort wasn't ignorance or mathematical error. It was intuition that this scenario violated the elegance and consistency he expected from natural law. We should have paid more attention to his resistance. Quantum mechanics reveals why. The classical picture of eternal imprisonment is incomplete. Imagine a cosmic library where books are constantly being locked in vaults that can never be reopened. As time passes, more and more volumes disappear behind impenetrable barriers. The library grows darker, emptier, more silent with each passing age. Eventually, all the interesting content, every story, every piece of knowledge, every record of what has been, becomes inaccessible. The library still exists, but it's functionally dead, its treasures entombed forever. This is how we've imagined the universe, with permanent black holes. But the universe doesn't operate this way. The vaults have timers. The locks eventually open. The books return, scrambled beyond recognition, perhaps transformed into nearly unreadable forms, but not gone forever. Black holes are temporary storage, not permanent prisons. This changes everything about how we understand cosmic information, entropy, and the ultimate fate of matter. When you hear "nothing escapes a black hole" in documentaries, articles, or casual conversations, you're witnessing cultural momentum, the classical understanding's persistence despite quantum corrections. Notice how confidently people state this fact. It demonstrates how incomplete pictures become accepted wisdom, how repetition creates the illusion of certainty. The pattern repeats throughout physics. Newtonian mechanics seemed complete until relativity revealed its limitations. Continuous matter seemed obvious until quantum mechanics exposed its discreteness. Absolute time appeared self-evident until Einstein showed it was observer-dependent. In each case, the classical picture wasn't wrong. It was incomplete. And in each case, the quantum or relativistic correction revealed deeper truth. Black holes follow this same pattern. The classical understanding that event horizons prevent escape is correct within its domain. General relativity's predictions about space-time curvature, gravitational time dilation, the inexorable pull towards singularities are all accurate. Light genuinely cannot escape classically. Objects falling inward genuinely cannot turn around and leave. The mathematics doesn't lie. But quantum mechanics operates by different rules than classical light propagation. Virtual particle pairs appearing at horizons behave in ways classical physics never predicted. The vacuum itself, which we think of as empty, turns out to be seething with quantum activity. When this quantum reality meets the extreme curvature of event horizons, something extraordinary happens. Black holes emit particles. They radiate energy. They shrink. They evaporate. The timescales are vast, incomprehensibly longer than the current age of the universe for stellar mass black holes. A black hole with the sun's mass would take roughly 10 to the 67th power years to disappear completely. This is so far beyond human experience, so much longer than the universe has yet existed, that for all practical purposes, these black holes are effectively permanent. But effectively permanent is not eternal. The principle is absolute, even if the timescales are absurd. No black hole is truly forever. This revelation isn't just a correction to popular understanding. It conceals an elegant truth about how the universe refuses to create permanent exceptions to its own rules. Quantum mechanics and general relativity, two extraordinarily successful theories that seem to contradict each other about black holes, must somehow both be right. Neither is disposable. Neither can be dismissed. The resolution requires understanding how they work together, how quantum processes operate in curved spacetime, how nature maintains consistency even in the most extreme circumstances imaginable. But wait, if black holes aren't permanent prisons, why did generations of physicists believe they were? Why did this misconception become so entrenched? The answer lies in understanding what general relativity actually predicts and why that prediction seemed unassailable for decades. Before we can grasp what black holes truly do, we must see why the classical understanding was so convincing and precisely where it breaks down. General relativity speaks with mathematical authority. Einstein's field equations describe how mass and energy curve spacetime and how that curvature determines the motion of matter and light. Near massive objects, spacetime warps like a rubber sheet depressed by a bowling ball. This analogy has become so familiar, it's almost cliché, but it captures something essential about gravitational attraction as geometric inevitability rather than mysterious force. For black holes, this curvature becomes extreme. Einstein's equations predict that if you compress enough mass into a small enough space, spacetime warps so severely that it creates a geometric trap with no escape routes. The event horizon, the boundary of no return, is where light cones tip completely inward. Every possible future directed path points toward the singularity at the center. Locally, nothing special happens as you cross the horizon. You wouldn't feel anything unusual, notice any barrier, encounter any resistance. But globally, you've entered a region where all paths lead inward. This is space-time geometry, not force, field blocking. The prediction is mathematically rigorous. It's been observationally confirmed through gravitational lensing, binary pulsar, orbital decay, and now direct gravitational wave detection from black hole mergers. The equations don't lie. Event horizons exist. Objects falling in cannot classically escape. Light itself, travelling at the universe's speed limit, cannot climb back out of the gravitational well. For decades, this seemed like the complete story. Yet quantum mechanics tells a different tale. The equations governing quantum evolution are unitary. They preserve information through time. If you know a system's complete quantum state at one moment, you can in principle calculate its state at any past or future moment. This reversibility is fundamental. Information is never created or destroyed, only transformed. The entire edifice of quantum theory rests on this principle. Quantum mechanics explains atomic spectra with extraordinary precision. It underlies all of modern chemistry, all of solid-state physics, all of the semiconductor technology that powers our computational age. It's been tested to incredible accuracy in countless experiments. The theory works. We rely on it every day in GPS satellites, medical imaging, computer processors, lasers, LED lights, and countless other technologies. Both theories are extraordinarily successful. But about black holes, they seem to contradict each other. General relativity says information falling past the event horizon is trapped forever, isolated from the outside universe, ultimately destroyed in the singularity. Quantum mechanics says information cannot be destroyed. The universe must remain reversible. Identical present states cannot arise from different histories. One theory demands isolation and destruction. The other demands preservation and reversibility. This isn't a minor discrepancy or a technical quibble. It's a fundamental contradiction about how reality operates. Imagine trying to navigate using two maps of the same city. One from street level, showing buildings and roads and traffic patterns. One from above, showing the urban layout from an aerial perspective. Usually these maps agree. Turn left at Main Street works from either viewpoint. The destination appears in the same place on both maps. Navigation proceeds smoothly because the maps describe the same underlying territory consistently. But suppose you encounter a region where the maps contradict each other. The ground level map says, no exits beyond this point. You cannot leave this district. The aerial map says, information about all streets must be preserved. There must be connections to the rest of the city. Both maps have been reliable elsewhere. You've used them successfully for years. Yet here, they give incompatible instructions. This is precisely the situation with black holes. General relativity, our ground-level map of gravity and space-time, says event horizons are one-way boundaries. Quantum mechanics, our aerial map of matter and information, says the universe must preserve its complete state. The maps contradict each other, signaling we need a unified map that reconciles both perspectives. We call this unified map quantum gravity, and we're still working on completing it. The contradiction creates genuine paradox because we can't simply declare one theory wrong. When you use GPS navigation, you're relying on general relativity corrections. Satellite clocks run differently than ground clocks due to both gravitational time dilation and velocity effects. Without these corrections, GPS would accumulate errors of several kilometers per day. The technology proves the theory's accuracy. When you use any electronic device with semiconductors, smartphones, computers, LED displays, solar panels, you're relying on quantum mechanics, the band structure that makes transistors possible, the quantum tunneling that limits how small we can make circuits, the electron behavior that enables computation. All of this emerges from quantum theory's predictions. Modern civilization would collapse without technologies based on quantum mechanical principles. Neither theory is disposable. Notice that in everyday life, you never need both simultaneously. Quantum effects matter for atoms and subatomic particles, but not for satellites orbiting Earth. Gravitational time dilation matters for GPS satellites, but not for the atomic behavior determining chemical reactions. The domains separate cleanly. For small things, use quantum mechanics. For massive things, use general relativity. For nearly everything in between, classical physics suffices. Black holes uniquely require both domains simultaneously. They're macroscopic objects, stellar, mass or larger, so general relativity must apply. But their event horizons create conditions where quantum effects at the smallest scales influence macroscopic behavior. This is extraordinarily rare. Most of the universe can be understood using either quantum mechanics or general relativity, but not both at once. Black holes exist precisely where both theories must apply, where neither alone suffices. This is why the contradiction remained hidden until careful theoretical work in the 1970s. Our everyday experience never tests the regime where both theories matter equally. We needed theoretical physicists working at the intersection of quantum field theory and general relativity to reveal what happens when quantum vacuum activity meets extreme spacetime curvature. Consider a thought experiment. Imagine you're watching your friend fall into a black hole. From your perspective outside, something strange occurs. As your friend approaches the event horizon, they appear to slow down. Time dilation becomes increasingly severe. They become more and more redshifted, their light stretching toward longer wavelengths as they approach the horizon. Asymptotically, they seem to freeze at the boundary, never quite crossing, becoming dimmer and redder, but never disappearing. From their perspective, the experience differs dramatically. They cross the event horizon in finite time, seconds or minutes, for a stellar, mass black hole. Nothing feels unusual at the moment of crossing. They plunge inward, falling toward the singularity where tidal forces eventually become infinite and physics as we know it breaks down. But the crossing itself isn't marked by any special sensation. Both perspectives are valid in general relativity. The mathematics accommodates both. Now add quantum mechanics to this picture. What happens to the quantum information about your friend's state? Every particle composing their body has a complete quantum state. Position, momentum, spin, all the quantum numbers that specify its behavior. Where does this information go? In classical general relativity, it falls into the black hole and is destroyed in the singularity. But quantum mechanics says this information must be preserved somewhere, somehow. The perspectives must reconcile. The theories must both be right. They don't reconcile. Not in classical theory. This isn't merely philosophical hand-wringing. Information conservation isn't abstract bookkeeping. It's fundamental to whether physics is deterministic, whether the universe has a unique history leading to the present, whether identical present states must have arisen from identical pasts. If information can be genuinely destroyed, then physics becomes fundamentally ambiguous. Multiple different histories could produce the same present state. Causality becomes slippery. The paradox forced physicists to look more carefully at what actually happens near event horizons when quantum mechanics is taken seriously. And what they discovered changes everything about how we understand these objects. The resolution requires understanding something strange about empty space itself. What we call vacuum, the absence of particles, the void between matter, turns out not to be empty at all. Quantum mechanics reveals that empty space seethes with activity at the smallest scales. This seemingly esoteric fact about vacuum fluctuations changes everything about black holes. To see how, we must first understand what supposedly empty space actually contains. Empty space should be nothing. This seems obvious, almost tautological. Remove all the particles, eliminate all the fields, Take away all the matter and energy, and you should be left with pure vacuum. Nothingness, absence, void. The intuition is so strong we rarely question it. Quantum mechanics says otherwise. Even in the lowest possible energy state, the quantum vacuum, fields cannot be perfectly still. Heisenberg's uncertainty principle forbids absolute stillness and zero energy simultaneously. The more precisely you try to specify that a field has exactly zero energy, the more uncertain its rate of change becomes. The field must fluctuate. This isn't a limitation of measurement or a gap in our knowledge. It's a fundamental feature of quantum reality. The quantum vacuum seethes with activity. Virtual particle, antiparticle pairs spontaneously appear, exist briefly on borrowed energy, then annihilate back into the vacuum before anyone can detect the energy loan. An electron and positron pop into existence, separate slightly, then find each other and annihilate. A quark and antiquark emerge, exist for the briefest possible instant, then disappear. Photon pairs flash in and out of existence. This happens everywhere, constantly, at scales too small and times too brief to observe directly. But the effects are real and measurable. Consider the Casimir effect, one of the most beautiful demonstrations of vacuum activity. Take two uncharged metal plates, no electrical charge, no obvious force between them, and place them very close, together in vacuum. A few micrometers apart, common sense says they should neither attract nor repel. They're uncharged. There's nothing between them. What could possibly push or pull them? They attract each other. The force is tiny, but measurable in laboratory experiments. Modern precision equipment can detect it clearly. And the explanation is purely quantum. The gap between the plates restricts which virtual particle wavelengths can exist there. Only certain wavelengths fit in the narrow space. Outside the plates, in the wider vacuum, all wavelengths of virtual particles contribute to the quantum fluctuations. This creates a difference in quantum vacuum pressure, more activity outside than inside. The plates are pushed together by the activity of supposedly empty space. This isn't philosophy. This is engineering, measured in laboratories, exploited in nanotechnology research. GPS satellites require quantum corrections. Every spontaneous emission of light from excited atoms involves virtual photons becoming real. The slight shifts in hydrogen spectral lines, the Lamb shift, arise from electrons interacting with vacuum fluctuations. When you observe fluorescence, radioactive decay, or use semiconductor devices exploiting quantum tunneling, you're witnessing quantum field fluctuations at work. The vacuum's activity isn't exotic. It's everywhere. Think of it this way. Imagine an ocean surface viewed from high above. From altitude, it appears smooth, a flat blue expanse stretching to the horizon. But zoom in and you see constant wave activity, ripples, foam, momentary peaks and troughs. The surface is never truly still. Zoom further to molecular scales, and you see individual water molecules in constant thermal motion, vibrating and colliding and exchanging energy. The quantum vacuum operates similarly. Smooth at large scales, we don't notice it in everyday life. But examine it at Planck scales, 10 to the minus 30, 5 meters, 10 to the minus 40, 4 seconds, and it's churning with constant particle creation and annihilation. This activity is always there, operating beneath the apparent calm of empty space. Virtual particles exist on borrowed time and energy, permitted by Heisenberg's uncertainty principle. The relationship is precise. The borrowed energy multiplied by the borrowed time must be less than Planck's constant. Larger energy borrowings require shorter time frames. A particle, antiparticle pair with significant mass can exist only for incredibly brief periods, typically Planck timescales, far shorter than anything we could ever hope to measure directly. This makes them virtual rather than real. But don't let the terminology fool you. They're genuinely quantum field excitations with genuine, measurable effects. They're not less real than regular particles. They're temporary disturbances in underlying quantum fields rather than permanent excitations. The distinction matters for the mathematics, but not for the physical consequences. These virtual particles don't violate energy conservation. The energy is borrowed from quantum uncertainty for time periods too brief to violate the uncertainty principle's limits. It's like borrowing money from a bank with a complex rule. You can borrow any amount you want, but the larger the loan, the shorter the repayment period. Borrow a small amount, and you might have it for a while. Borrow a huge amount, and you must repay it almost immediately. The bank's accounting always balances. The quantum vacuum is that bank. Virtual particles are the loans. Now imagine a casino where you can borrow chips under similar rules. The more chips you borrow, the shorter your loan period. Normally, you must return them before security notices. You borrow chips, use them momentarily at a table, then immediately repay the debt before anyone can detect the loan. This works fine throughout the main casino floor. The borrowing and repayment happen so quickly that the casino's inventory never shows a deficit. But near the exit, imagine the event horizon of a black hole. Something remarkable happens. If you borrow your chips right at the exit, one person in your party might get outside with them before the other person can catch up to settle the debt. The exit, the event horizon, prevents reunion. One person escapes with chips, the other person inside no longer has a partner to complete the transaction with. The casino loses those chips permanently. They've become real losses, no longer temporary borrowing. The quantum vacuum is that casino. Virtual particles are the borrowed chips. The event horizon is the exit that separates borrowers irreversibly. In flat space, far from any black hole, particle pairs appear and quickly reunite to annihilate. The separation distance remains microscopic. Quantum uncertainty allows brief separation, but the particles find each other and settle the energy debt before the loan period expires. The vacuum's accounting balances perfectly, but if a pair appears with one member just inside an event horizon and one member just outside the horizon's one-way nature prevents reunion. The particles cannot find each other to annihilate. The separation becomes permanent. The quantum process that created them becomes a real particle production event, powered by the black hole's gravitational field. One particle escapes into space, the other falls toward the singularity. They can never reunite. The energy loan cannot be repaid. The particles have become real. This is Hawking radiation, real particles emerging from quantum vacuum activity at event horizons. You now possess the conceptual tool needed to understand how black holes evaporate. Empty space has become quantum foam in your understanding, constantly active at microscopic scales with genuine physical consequences. You understand that vacuum activity is experimentally verified through the Casimir effect and countless other quantum phenomena. This isn't speculation or philosophical interpretation. This is demonstrated physics. When this quantum vacuum activity occurs at an event horizon, where spacetime geometry prevents virtual pair reunion, the mechanism for black hole radiation reveals itself. We now understand that the vacuum constantly produces virtual particle pairs. We understand that black hole event horizons are one-way boundaries in spacetime. When these two facts combine, something extraordinary happens. The mechanism of black hole evaporation becomes clear. Let's see precisely how it works. Virtual particle pairs appear at event horizons just as they appear everywhere else. Quantum vacuum fluctuations don't stop operating because gravity becomes intense. If anything, the extreme conditions might enhance certain quantum effects. But the crucial factor isn't enhancement, it's separation. When a particle pair appears with one member just inside the event's horizon and one member just outside, they face an insurmountable geometric barrier. The horizon is a one-way boundary in space-time, a surface where the light cones tip completely inward. The particle inside cannot reach the particle outside because all future directed paths lead toward the singularity. The particle outside cannot reach the particle inside without crossing the horizon itself and becoming trapped. The pair cannot annihilate. The separation becomes permanent. From the outside universe's perspective, the black hole has just emitted a particle. One member of the pair escapes as real radiation, flying away into space. This is Hawking radiation, real particles emerging from quantum processes at the boundary of extreme space-time curvature. But wait, didn't the black hole just gain a particle? The one that fell in? How is this radiation? How does the black hole lose mass? Here's the crucial and deeply counterintuitive bit. The in-falling particle carries negative energy relative to outside observers. This sounds impossible. Energy is energy. How can it be negative? But in general relativity, energy isn't an absolute quantity. It depends on reference frame and coordinate system. In flat space-time, far from any gravitating bodies, we can define energy unambiguously relative to infinity. But in curved space-time near a black hole, reference frames become twisted by extreme gravity. Think of debt as negative wealth. If someone escapes a building carrying cash while someone inside simultaneously accumulates debt, the building's total wealth decreases even though nothing obviously left carrying value. The person outside has money, positive wealth. The person inside owes money, negative wealth. The building is poorer overall. The accounting balances perfectly when you include negative numbers. Black holes work similarly at the quantum level. The escaped particle carries positive energy. It's a real particle moving through space with kinetic energy and mass, energy we can measure. The infalling particle carries negative energy relative to observers at infinity. This is possible in curved spacetime near horizons because energy measurements depend on reference frame, and the extreme curvature means different reference frames disagree dramatically about what energy means. The black hole's total mass, energy, as measured from outside, decreases by the amount of positive energy that escaped. The black hole pays for the radiation with its own mass. This isn't metaphor or approximation. This is the precise quantum field theory calculation in curved spacetime. The mathematics is complex. Combining quantum field theory with general relativity requires sophisticated techniques, but the principle is clear. Virtual particle separation at horizons produces real particles through a process that conserves energy by allowing negative energy states in the extreme gravitational field. Energy is conserved globally. Black holes shrink. You might object that this still seems wrong. How can a particle inside a black hole have negative energy? Surely energy must be positive. It's the capacity to do work, to create change, to have effects. Negative energy seems like mathematical trickery, but you experience reference, frame, dependent energy constantly. When you're in a moving car, objects outside have kinetic energy relative to you. From the ground frame, you have kinetic energy. Neither frame is right. Energy genuinely depends on the observer. Near black holes, this principle becomes extreme. GPS satellites prove the point. Time and energy are measured differently in different gravitational fields. Satellite clocks run faster than ground clocks by about 38 microseconds per day due to weaker gravity at altitude, slower by about 7 microseconds per day due to orbital velocity. The net gain of about 31 microseconds might seem trivial, but it would accumulate to GPS position errors of 10 kilometers per day without corrections. Every time GPS recalculates your position, it's correcting for reference frame dependent measurements of time and energy. The mathematics is standard relativity. Black holes push this principle to extremes, but the underlying concept, that energy depends on reference frame, is thoroughly familiar and constantly verified. Near an event horizon, the curvature becomes so extreme that particles inside can have negative energy from the perspective of observers at infinity. This isn't a loophole or mathematical trick. It's how energy conservation works in general relativity when spacetime curves severely. Imagine you're stationed just outside the event horizon with sophisticated equipment. You observe virtual particle pairs forming from vacuum fluctuations, the quantum foam we discussed earlier. One member falls inward, the other flies outward. From your nearby perspective, energy must be conserved locally. The outward particle has positive energy. Therefore, the inward particle must carry negative energy to balance the books. This seems wrong only if you forget that energy near the horizon means something different than energy at infinity. Reference frames tilted by extreme gravity change what energy measurements mean. The particle inside genuinely has negative energy relative to distant observers, even though locally everything appears normal. The process is continuous and inevitable. Virtual pairs appear constantly at all scales. Near the horizon, this constant quantum activity translates into steady particle emission. Black holes cannot avoid this. It's built into quantum field theory in curved spacetime. Wherever you have both quantum fields and curved spacetime, you get particle production through this mechanism. Black holes don't violate quantum mechanics or general relativity. They demonstrate how both theories work together. The classical picture wasn't wrong about event horizons preventing escape. Nothing crosses the horizon outward, but it was incomplete about quantum processes near horizons. People often imagine particles tunneling out of black holes. This is incorrect. Nothing crosses the event horizon outward. Instead, particles form just outside the horizon from quantum vacuum processes. The black hole doesn't shoot out radiation like a gun. The radiation emerges from quantum field behavior in the black hole's gravitational field. The mechanism is counterintuitive, but logically consistent. Virtual particle pairs at horizons become real through geometric separation. The infalling particle carries negative energy. The black hole's mass decreases. Energy is conserved perfectly when you account for all the relativistic subtleties. Black holes emerge as dynamic quantum objects, not static classical structures. But if black holes emit particles, they must have temperature. Radiation and temperature are inseparable in thermodynamics. Any object that radiates must have a characteristic temperature related to its emission spectrum. This means black holes aren't exceptions to physics, but full participants in the universe's thermodynamic evolution. The implications are extraordinary. Let's explore what temperature means for objects defined by preventing escape. Temperature and radiation are linked by fundamental thermodynamics. Hot objects glow. This is everyday experience. A stove element glows red when moderately hot, white hot at higher temperatures. The sun's surface at roughly 5,800 Kelvin appears yellow, white. Your body radiates infrared at about 310 Kelvin, which is why thermal cameras can see you in darkness. The relationship between temperature and emission spectrum, black body radiation, is universal. All objects radiate according to their temperature. This isn't a property of matter alone. It's a consequence of thermodynamics and quantum statistics. Black holes follow identical principles. If black holes emit Hawking radiation through quantum processes at their event horizons, they must have temperature. The question is, what temperature? The calculation reveals something remarkable. Temperature is inversely proportional to mass. Double the black hole's mass, halve its temperature. Make it 10 times more massive, make it 10 times colder. The precise formula involves fundamental constants. The Hawking temperature equals Planck's constant times the speed of light cubed, divided by 8 pi times the gravitational constant times the black hole's mass times Boltzmann's constant. It's a beautiful equation connecting quantum mechanics, relativity, thermodynamics, and gravity in a single expression. For a black hole with the sun's mass, the temperature is about 60 billionths of a Kelvin. This is extraordinarily cold, far colder than anything we can achieve in laboratories, far colder than the coldest places in the observed universe, millions of times colder than the cosmic microwave background radiation that fills space. A solar, mass black hole is, paradoxically, one of the coldest objects imaginable, but the relationship between mass and temperature creates a feedback loop with profound consequences. A black hole with a mountain's mass would glow white, hot, temperatures exceeding billions of Kelvin. A black hole the size of a proton would have temperatures approaching the Planck temperature, 10 to the 30, 2 Kelvin, hot enough that our current physics breaks down trying to describe it. As black holes shrink, they heat up dramatically. This creates runaway evaporation. As the black hole radiates, it loses mass. As it loses mass, its temperature increases. As temperature increases, radiation rate increases. As radiation rate increases, mass loss accelerates. The feedback loop compounds. Smaller means hotter. Hotter means faster radiation. Faster radiation means shrinking more quickly. Imagine ice that gets hotter as it melts. Ordinary ice melts at constant temperature, absorbing heat from its environment. But imagine ice where the melting process itself generated heat, and the smaller the remaining ice, the faster it heated up. The last gram would explode in sudden, intense heat. This is black hole evaporation, starting unimaginably slowly, but ending explosively. The timescales are absurd. A solar mass black hole would take roughly 10 to the 67 years to evaporate completely. Let's put this in perspective. The universe is roughly 13.8 billion years old, about 4 times 10 to the 17 seconds. A solar mass black hole's evaporation time is 10 to the 67th years, or about 3 times 10 to the 74 seconds. That's 10 to the 50, 7 times longer than the universe's current age. If the universe's age were 1 second, the evaporation time would be 10 to the 57 seconds, which itself is longer than the current age of the universe. The scales are incomprehensible, yet the principle holds: they evaporate. Currently, stellar black holes absorb more than they emit. The cosmic microwave background radiation has a temperature of about 2.7 Kelvin. A solar mass black hole at 60 billionths of a Kelvin is millions of times colder. It absorbs far more CMB photons than it emits through Hawking radiation. The universe is too hot for stellar black holes to shrink. Only in the far future, when the universe cools below a black hole's temperature, will that hole begin net evaporation. For solar, mass black holes, this happens after the CMB cools below 60 nanokelvin, when the universe has expanded enough that the background radiation stretches to longer wavelengths and lower temperatures. Then evaporation begins in earnest. Most of the black hole's lifetime is spent at nearly constant large mass. The radiation rate is fantastically slow. Effectively, nothing happens for incomprehensible durations. But as the black hole finally shrinks to modest masses, planetary mass, then mountain mass, then smaller, the evaporation accelerates dramatically. The final kilogram evaporates in a tiny fraction of a second. When a black hole shrinks to roughly the Planck mass, about 2 micrograms, roughly the mass of a biological cell, it radiates with incredible intensity. Temperature approaches 10 to the 32 Kelvin. The final explosion releases the remaining mass, energy in a burst of high-energy particles and radiation. The most stable, seeming structures in nature end violently. The universe doesn't care about our preferences for drama or anticlimax. Of course, waiting 10 to the 67 years for a solar mass black hole to evaporate requires considerable patience. The universe may not have such patience, but the principle stands regardless. Black holes are thermodynamic objects with temperature, radiation, and finite lifetimes. No black hole is permanent. This transforms our understanding profoundly. Black holes aren't eternal monuments, but temporary structures, counting down to inevitable disappearance. They participate in cosmic thermal evolution, objects that cool when they grow larger. Temperature drops with increasing mass. Heat when they shrink. Temperature rises with decreasing mass, and eventually vanish entirely through quantum evaporation at their boundaries. The timescales might be vast, but the principle is absolute. Everything we've learned points to black holes as fully integrated into the universe's thermodynamic processes, following the same laws that govern melting ice and cooling coffee, radiating according to their temperature, just like any other hot object. But this raises a profound puzzle that cuts to the foundations of physics itself. If black holes emit purely thermal radiation, random heat with no structure or correlations, then information about what fell into the black hole appears lost forever. Yet quantum mechanics insists information cannot be destroyed. The universe must be reversible in principle. These requirements contradict each other. This is the information paradox, and resolving it requires rethinking what black holes fundamentally are. When you burn a book, the information seems lost. The words become ash and smoke. The organization becomes disorder. The carefully arranged sentences dissolve into chemical chaos. Carbon dioxide dispersing into the atmosphere, carbon residue scattered as powder, heat radiating into the surroundings. Anyone looking at the aftermath would struggle to reconstruct what was written. But physics says the information isn't actually destroyed. A perfect demon, an imaginary being with unlimited computing power and perfect knowledge of every particle's position and momentum, could in principle reconstruct exactly what was written. By tracing every molecule's trajectory backward through time, tracking every atom's path from ash back through combustion to organize cellulose and ink, the demon could recover the complete text. The information is scrambled, not destroyed. Physics permits reconstruction even if practical impossibility prevents it. This is a crucial distinction. When we say information is scrambled, we mean it's still there in the system's quantum state, just thoroughly mixed and dispersed. Recovery would require tracking an astronomical number of particles with impossible precision. Practically, it's beyond any technology we could ever build. But in principle, according to the fundamental laws of quantum mechanics, the information survives. Black holes threaten this principle. If Hawking radiation is purely thermal, completely random with no structure, no correlations between emitted particles, then information about what fell into the black hole appears irretrievably lost, not just scrambled beyond practical recovery, but genuinely erased from existence. A book falling into a black hole would eventually become thermal radiation, carrying no trace whatsoever of what was written. The radiation from a black hole that consumed a book would be indistinguishable from radiation from a black hole that consumed the same mass of hydrogen gas. Thermal radiation is maximum entropy. Every possible microstate is equally probable. It's heat, pure disorder, with no information content beyond the total energy. If Hawking radiation is exactly thermal, then whether the black hole formed from a collapsing star, from compressed antimatter, or from a library of ancient manuscripts, the radiation would be identical. The past would be genuinely unknowable. This would violate quantum mechanics at its foundation. Quantum mechanical evolution is unitary. This technical term means information, preserving. If you know a system's complete quantum state, the detailed specification of every particle's quantum properties, you can calculate its state at any past or future time. The mathematics is reversible. Information flows forward through time, but never disappears. This reversibility isn't philosophical, preference, or aesthetic choice. It's built into the structure of quantum theory. Black holes destroying information would break this cornerstone principle. Initially, many physicists accepted that perhaps information might actually be destroyed in black holes. Perhaps quantum mechanics failed in strong gravity. Perhaps the rules changed at event horizons. Perhaps the universe had legitimate exceptions where information could genuinely disappear. The alternative, that somehow information escaped in the thermal radiation, seemed mathematically impossible given the calculations. But as understanding deepened, accepting information destruction became untenable. Quantum mechanics is too successful, too thoroughly tested across too many contexts. The theory explains atomic structure, chemical bonding, superconductivity, quantum computing, particle physics, and countless phenomena with extraordinary precision. Every technology exploiting quantum effects, semiconductors, lasers, magnetic, resonance imaging, atomic clocks, quantum cryptography, confirms the theory's predictions. The mathematical framework has been verified to incredible accuracy. If quantum mechanics breaks down for black holes, then we lose confidence in a theory that works everywhere else. The intellectual cost becomes enormous. The consensus shifted. Information must be preserved somehow, even if the mechanism remains unclear. The paradox isn't pedantic bookkeeping. It's fundamental to whether physics is consistent and deterministic. Consider what information destruction would actually mean. If identical present states could arise from different histories, if a black hole's current state doesn't uniquely determine its past, then the universe becomes fundamentally ambiguous. Causality becomes slippery. The past becomes not just unknown, but genuinely unknowable, even in principle. Physics loses its predictive and retrodictive power. Information theory underlies all of modern computation and communication. Cryptography relies on information being fundamentally conservable, even if practically irretrievable. Quantum computing exploits unitarity. Reversible quantum gates that preserve information while processing it. Error correction in computer memory, data compression algorithms, Shannon's communication theory, all assume information cannot simply disappear, only be scrambled, compressed, or encrypted. When you delete a file from a hard drive, the data becomes difficult to access but isn't actually destroyed. Forensic recovery exploits this fact. The magnetic domains retain their states until explicitly overwritten. The information persists in the system even when you can no longer easily retrieve it through normal channels. The information paradox asks whether these principles remain true in the most extreme circumstance imaginable, when matter crosses an event horizon and the black hole eventually evaporates. If information can be destroyed anywhere in the universe, the foundations of information science wobble. Everything we think we understand about how data, memory, computation, and communication work might require revision. Notice that every digital technology assumes information conservation. Your computer's operation depends on bits maintaining their states reliably. Your phone's storage assumes written data persists. Internet communication assumes transmitted information arrives intact. These aren't just engineering conveniences, they reflect deep physical principles about how information behaves in quantum systems. The paradox creates genuine intellectual discomfort. Two extraordinarily successful theories, quantum mechanics and general relativity, give contradictory answers about black holes. Thermal radiation seems to imply information loss. Unitarity demands information preservation. Both seem necessary, yet they appear incompatible. This is frontier physics, unsolved in its details. Several possible resolutions remain speculative. Perhaps information encodes in subtle correlations between Hawking radiation particles, correlations so delicate they appeared thermal in initial calculations but actually preserve information in quantum entanglement between emitted particles. Perhaps the final explosion, when the black hole evaporates, completely releases information that was stored somehow in the black hole's quantum state. Perhaps event horizons have quantum structure we don't yet understand. Fuzzball proposals or holographic surface states that preserve information. We don't know which, if any, of these is correct. What we do know is that the physics community's consensus has shifted. Information must be preserved. The mechanism remains unclear, but the principle seems non-negotiable. The alternative, that quantum mechanics fails for black holes, creates more problems than it solves. Better to accept that we don't yet fully understand how information escapes than to abandon a theory that works everywhere else. This isn't satisfying in the way resolved questions are satisfying. Scientists don't enjoy admitting ignorance, but on this question, honesty requires it. We believe information survives black hole evaporation. We're working to understand precisely how. The mathematics is challenging. The physics pushes our theories to their limits. But the very existence of this paradox teaches us something profound. Black holes are probes of physics' deepest principles. They reveal where our current theories strain, where new understanding is needed, where quantum mechanics and gravity must merge into something more complete. The information paradox isn't a failure of physics, it's a signpost pointing toward quantum gravity, toward whatever theory eventually unifies our understanding of matter and space-time. Unsolved questions become intellectually exciting rather than frustrating when we recognize them as opportunities for discovery. But black holes revealed something else extraordinary in the process of creating this paradox, something about how information and space itself relate. They have entropy proportional to their event horizon's surface area, not their volume. This bizarre scaling hints at something profound about space-time's fundamental nature. It suggests our three-dimensional reality might be more like a projection than the straightforward space it appears to be. Entropy is a measure of disorder, of how many different microscopic arrangements could produce the same macroscopic state. For ordinary objects, entropy scales with volume. More space means more possible arrangements. Double the size of a gas-filled container in all directions, you increase the volume eightfold, and the entropy increases roughly eightfold as well. This makes intuitive sense. More room means more possible positions for particles, more possible configurations, higher entropy. Black holes break this pattern spectacularly. The Bekenstein-Hawking entropy, the entropy associated with a black hole, is proportional to the event horizon's surface area, not the enclosed volume. The formula is precise. Entropy equals 1/4 of the horizon area measured in Planck units, multiplied by Boltzmann's constant. Double the black hole's radius, you quadruple the surface area, and you quadruple the entropy. But the volume increases eightfold. This is deeply counterintuitive. Imagine cataloguing all possible arrangements in a library, all the different ways you could organize books, all the possible texts that could be written, all the configurations of matter and information. Intuitively, the library's capacity depends on volume. How many books fit inside? How much three-dimensional space is available for storage? Double the floor space and double the shelf height. You quadruple the area of the walls and floor. But you've increased the volume eightfold. You could fit 8 times as many books. The capacity should scale with volume, not surface area. Black hole entropy says no. It depends on wall space, the surface area of the boundaries. This is peculiar enough that it demands explanation. What could it possibly mean that information content scales with boundary area rather than interior volume? For ordinary matter, this makes no sense. A box containing gas has entropy proportional to how much gas fits inside, not to the box's surface area. The molecules move through the full three-dimensional volume. Information is stored throughout the interior, but for black holes, entropy scales with area. This difference suggests black holes reveal something fundamental about how information relates to space itself. The insight emerged from careful analysis of black hole thermodynamics in the 1970s. If black holes have temperature and radiate, they must have entropy. Thermodynamics demands it. The calculation revealed the area dependence, and this discovery opened doors to entirely new ways of thinking about spacetime. For any region of space with fixed volume, the maximum entropy that region can contain is achieved by filling it with the largest black hole that fits. And that maximum entropy is proportional to the region's surface area, not its volume. This suggests something profound. Information content is fundamentally bounded by surface area. The holographic principle emerged from this realization. If maximum information scales with area rather than volume, perhaps information is actually encoded on boundaries rather than interiors. Perhaps three-dimensional space is like a hologram, apparently three-dimensional, but fundamentally two-dimensional in its information content. The interior volume might be reconstructed from boundary information, much like a holographic image creates the illusion of depth from information stored on a flat surface. When you view a hologram, you see three-dimensionality. You can move your head and see parallax. Objects appear to have depth, to exist in layers front to back. Yet, all the information creating this three Dimensional experience is stored on a two-dimensional surface. The depth is reconstructed by your visual system from patterns of light coming from a flat hologram. The holographic principle suggests something similar for the universe itself. Our three-dimensional experience, the sense of moving through space in three independent directions, the perception of objects with length, width, and depth, might be encoded on two-dimensional boundaries. The interior might be emergent, reconstructed from boundary information according to physical laws. This sounds like science fiction, but it emerges naturally from taking black hole entropy seriously. String theory made this concrete through the AD-CFT correspondence, anti-de Sitter, conformal field theory correspondence, discovered by Juan Maldacena in 1997. This is an exact mathematical equivalence between gravity in certain curved spacetimes and quantum field theory on their boundaries. Holography made mathematically precise. Black hole entropy provided the crucial hint that led theoretical physicists toward this breakthrough. The correspondence shows that in specific spacetime geometries, everything happening in the interior, gravity, matter, energy, all physical processes, can be exactly described by a quantum field theory living on the boundary. The three-dimensional interior, actually five-dimensional in AD-CFT, but the principle holds, is completely encoded in the lower dimensional boundary theory. This is extraordinary. It suggests that the spatial dimension we experience might be somehow emergent or encoded rather than fundamental. Now, we must be careful about over-interpreting. The holographic principle doesn't mean the universe is a simulation or we're living in the matrix. It's about how information and geometry relate in quantum gravity. It's about the surprising fact that spatial volume's information content is bounded by surface area rather than volume itself. And the principle isn't proven for our actual universe. AD-CFT works for anti-de Sitter spaces, geometries with negative cosmological constant, not like our universe, which appears to have positive cosmological constant and accelerating expansion. Whether holography applies to our cosmos remains an open question. But the principle suggested by black hole entropy has profound implications regardless. Think about information storage limits. You might imagine packing hard drives ever more densely, compressing data using ever more sophisticated algorithms, even using quantum storage to pack information at atomic scales. But there's a fundamental limit. If you pack too much energy into a finite region, and information has energy through Einstein's mass-energy equivalence, the region collapses into a black hole. And that black hole's entropy, its information content, depends on the region's surface area, not its volume. The maximum information you can store in a box scales with the box's boundary, not its interior. This is a fundamental limit, not a technological constraint. It suggests something deep about how space and information relate at the quantum gravity level. Consider trying to store maximum information in a cubic meter. You pack in hard drives, compress data, use quantum superposition, employ every trick imaginable. But eventually, if you add too much mass, energy, the cube collapses into a black hole. And that black hole's entropy, measured in bits of information, equals 1/4 of its horizon area in Planck units. The maximum information in the cubic meter is determined by how much surface area the eventual black hole would have, not by the cubic meter's volume. Space itself has maximum information capacity proportional to area. Black holes emerged as more than extreme gravitational objects. They're revelatory about spacetime's fundamental nature. The area scaling of entropy isn't a curiosity or coincidence. It's a clue that three-dimensional space might emerge from two-dimensional information in ways we're still working to fully understand. Studying the most exotic conditions reveals hints about everyday space's deep structure. The holographic principle, suggested by black hole thermodynamics and made mathematically concrete in string theory, has reshaped how theoretical physicists think about space, time, and information. It's changed the questions we ask about quantum gravity and the nature of reality. This is what black holes teach us when we pay careful attention to their thermodynamics. They're not monsters outside physics. They're windows into the deep structure of the universe, revealing connections between quantum mechanics, gravity, thermodynamics, and information theory that reshape fundamental physics. We've journeyed from misconception through mechanism to paradox to holography. We understand what black holes do and what they reveal about reality's structure. But what does all this mean for the universe's ultimate fate? If all black holes eventually evaporate, the cosmos' distant future looks different than classical physics imagined. Everything they've consumed returns, albeit transformed beyond recognition. The classical picture of black holes accumulating forever created a peculiarly bleak cosmos. As stars collapsed, as matter fell past event horizons, as black holes merged and grew, an increasing fraction of the universe's interesting content would become locked away behind impenetrable barriers. Stars, planets, entire galaxies eventually succumb to gravitational imprisonment. In the far future, the universe would contain vast black holes surrounded by increasingly empty space. Everything interesting gets archived behind event horizons forever. Hawking radiation changes this picture completely. If all black holes eventually evaporate, then everything they've consumed eventually returns to the universe as radiation, not in its original form. The radiation is thermal, maximum entropy, essentially useless energy. But the matter and energy aren't locked away permanently. The prisons have time limits. Given enough time, incomprehensible durations, yes, but finite nonetheless. Every black hole surrenders its contents back to the cosmos. Return to the cosmic library metaphor we introduced at the beginning, now transformed by everything we've learned. Instead of books being locked permanently in vaults that never open, imagine a library where volumes are temporarily encrypted in unreadable form but eventually decoded. The decoding takes extraordinarily long, patience measured in 10 to the 67 years for solar mass black holes. But the library never loses a book permanently. Every story returns, though scrambled. Every word survives, though jumbled. The universe is a library with perfect conservation but imperfect organization. Black holes are the filing system's temporary storage, long-term archival with eventual retrieval, even if the retrieval process scrambles the contents into maximum disorder. Information is preserved, somehow. We're still working out the mechanism, but organization is lost. Order becomes disorder. Structure becomes chaos. But nothing accumulates permanently behind horizons. The timescales are vast beyond human comprehension. Stellar black holes, those formed from collapsed stars, have masses between roughly 3 and 100 solar masses. The smallest would take about 10 to the 67 years to evaporate. The largest might take 10 to the 69 years. These durations dwarf the universe's current age of roughly 10 to the 10 years. We're talking about timescales 10 to the 50, 7 times longer than the universe has yet existed. Supermassive black holes, the giants lurking in galactic centers, make these timescales seem brief by comparison. 1 million solar mass black hole would take about 10 to the 83 years to evaporate. Billion solar mass monster might last 10 to the 92 years. The largest known black holes, tens of billions of solar masses, would persist for 10 to the 100 years or longer. Yet, eventually, still means eventually. In the inconceivably distant future, long after the last stars have burned out, long after galaxies have dissipated, long after protons themselves may have decayed, black holes will be evaporating. They'll be the last significant structures remaining, and then they too will disappear, returning their contents as radiation into the cold, dark, unimaginably expanded cosmos. The universe doesn't create permanent information prisons, it creates temporary ones. This changes the cosmological picture fundamentally. Instead of matter progressively accumulating in permanent gravitational traps, everything eventually returns. The universe becomes increasingly entropic, more disordered, more uniform, more diffuse, but not increasingly unknowable. The secrets, locked behind event horizons, eventually emerge, transformed but not destroyed. Black holes are extraordinarily efficient entropy engines. They take organized matter, stars with nuclear fusion processes, planets with geological activity, potentially even civilizations with information processing, and convert it into nearly thermal radiation. Maximum disorder, minimum information density. As black holes form, grow, and eventually evaporate, they accelerate the universe toward maximum entropy. This connects directly to the arrow of time, why time flows forward, why we remember the past, but not the future, why coffee cools rather than spontaneously heats. Entropy increase explains temporal directionality. The second law of thermodynamics states that entropy in closed systems increases over time. This isn't just a statistical tendency. It's fundamental to how we experience time's passage. Black holes follow this same arrow, radiating entropy into the cosmos. They're fully integrated into thermodynamics' universal reach, not exceptions to it. Mountains erode grain by grain. Stars burn out after billions of years. Species go extinct. Memories fade. Relationships transform. Nothing you can name remains unchanged forever. We intuitively understand impermanence in our lives. Everything we build, love, or create will eventually change or disappear. Black hole evaporation extends this principle to the most extreme structures imaginable. Even gravitational prisons held together by space-time curvature, objects where escape velocity exceeds light speed, where classical physics says nothing leaves ever, eventually dissolve through quantum processes. The most stable seeming structures are actually slowly self-destructing at their boundaries. Quantum mechanics defeats even the most extreme gravitational confinement given sufficient time. Notice how universality appears throughout this understanding. No exceptions, no escape clauses, no permanent fixtures in the cosmos. The universe is transient all the way down, from subatomic particles that decay, to stars that burn out, to black holes that evaporate, to the universe itself that expands and cools toward maximum entropy. This could seem depressing. Nothing lasts, everything ends, impermanence is absolute. But there's another way to think about it. Impermanence makes change possible, makes evolution possible, makes transformation possible. Static permanence would be stagnation. A universe where black holes truly lasted forever, accumulating information behind barriers that never yielded, would be a cosmos frozen in its complexity. unable to fully explore the space of possible states. Instead, we find a universe that recycles, that transforms, that moves inexorably toward maximum entropy whilst preserving the total information content somehow, even through the most extreme processes. In the far future, after all black holes have evaporated, the universe becomes extraordinarily diffuse and cold. The cosmic microwave background radiation stretches to ever longer wavelengths as space expands. Temperature approaches absolute zero asymptotically, but the diffuse radiation includes everything that once was locked behind event horizons. The black holes return their contents. The prisons opened. Whether anything complex or interesting can exist in such a universe is an open question. Perhaps not. Perhaps the far future is genuinely dead, incapable of supporting structure or life or thought. The heat death of the universe, maximum entropy, thermal equilibrium at temperatures approaching zero. But it's a heat death without permanent information prisons, without locked vaults that never open. The universe doesn't create regions where information goes to die forever. It creates temporary structures, however long, lasting, that eventually return what they've taken. This reveals the cosmos as fundamentally transient and transformational. Nothing is permanent, not matter, not energy, not even the event horizons that seemed like ultimate boundaries. Everything transforms, everything returns to the universe in altered form. Black holes, which appeared to be the exception to this rule, turn out to be its ultimate proof. We've seen what black holes teach us about permanence, information, and cosmic evolution. But the deepest lesson remains that we can understand black holes at all. That primates on an ordinary planet can comprehend the behavior of the most extreme objects in existence through mathematics, reason, and careful inquiry. This itself is remarkable beyond measure. The universe maintains logical consistency even in the most extreme circumstances. This is not obvious. Nature could be chaotic, arbitrary, inconsistent. The laws of physics could change from place to place, from scale to scale, from condition to condition. We might live in a cosmos where different rules apply in different contexts, where exceptions proliferate, where no unified understanding is possible. Instead, we find deep coherence. Rather than create exceptions where quantum mechanics fails or where general relativity breaks down, nature finds mechanisms preserving both theories, however subtle, however counterintuitive. Hawking radiation exemplifies this beautifully. Black holes emit particles through quantum processes at their event horizons. They conserve energy through general relativistic negative energy states. Both theories are respected. Both theories prove necessary. Neither is violated. The same thermodynamic principles that explain why your morning coffee cools also explain why black holes evaporate. The same mathematics describing ice melting describes black hole temperature and radiation. The same quantum field theory predicting atomic transitions predicts particle production at horizons. There are no separate rules for separate domains. One consistent framework extends across all scales, from the subatomic to the cosmic. Physical law shows profound unity. The same information theory underlying computer science concerns physicists debating black hole information paradoxes. The same mathematical structures describing electromagnetic waves describe gravitational waves. The same statistical mechanics governing gas pressure governs black hole thermodynamics. This unity isn't guaranteed by logic. It's a profound feature of our universe that demands explanation. We find ourselves in a cosmos that speaks mathematics. The relationships governing phenomena from quantum fluctuations to cosmic expansion can be expressed in equations. These equations connect to each other, build on each other, constrain each other. The mathematical consistency often predicts new phenomena before observation confirms them. Antimatter predicted by Dirac's equation. The Higgs boson predicted by symmetry principles. Gravitational waves predicted by Einstein's field equations. The universe is comprehensible. This is extraordinary. Nature could have been incomprehensible, too complex for any pattern recognition, too chaotic for mathematical description, too arbitrary for predictive models. Instead, we've discovered that studying nature through careful observation, experimentation, and mathematical reasoning yields genuine understanding. Not complete understanding, we're far from that, but genuine insight into how reality operates at its deepest levels. Black holes make this especially clear because they're so extreme. We have no direct human experience of event horizons. No one has visited a black hole and returned to describe it. We cannot observe Hawking radiation from stellar mass black holes. The effect is far too weak, given their incredibly low temperatures. We're discussing objects millions of times more massive than Earth, with gravitational fields so intense they warp spacetime beyond everyday intuition, operating on timescales exceeding the universe's age by factors of 10 to the 57. Yet we can understand them. Through reason and mathematics alone, we've determined that black holes have temperature inversely proportional to their mass, that they radiate through quantum processes at their boundaries, that their entropy scales with horizon area, that they eventually evaporate entirely, that they participate in the same thermodynamic laws governing ice cubes and steam engines. None of this is guesswork or speculation. It follows necessarily from combining quantum field theory with general relativity. We are made of atoms forged in stellar cores, assembled by chemistry and evolution, arranged by billions of years of cosmic history into structures capable of contemplating the universe that made us. Think about what's actually happening when you understand a concept about black holes. Atoms in your brain, carbon, hydrogen, oxygen, nitrogen, mostly, are processing mathematical relationships. These atoms were created in stars that burned and died billions of years ago. They've journeyed through space, been incorporated into the solar system's formation, assembled into your body through biological processes, organized into neural networks capable of abstract thought. And now, those atoms are modeling phenomena at the edge of space-time. When you grasp why black holes have temperature, atoms from long-dead stars are comprehending thermodynamics in curved space-time. When you understand Hawking radiation, you're employing quantum field theory, one of nature's deepest mathematical structures, to reason about objects where space and time exchange roles. The universe is not only comprehensible, it has created subsystems, us, capable of comprehending it. We are the universe's way of knowing itself. This is as profound as any physical law we've discovered. Consciousness, mathematics, scientific inquiry. These are ways the cosmos explores its own nature. When we understand black holes, it is the universe understanding itself through us. We're not separate observers examining nature from outside. We're nature examining itself from within. Every time you grasp a scientific insight, you're participating in this cosmic self. Reflection. When you understand why the sky is blue, Rayleigh scattering of shorter wavelengths, you're experiencing what makes us remarkable. When you comprehend why water freezes at 0 Celsius, hydrogen bonding creating ice's crystal structure, atoms in your head are understanding atomic behavior. When you grasp why planets orbit stars, gravity balancing or orbital momentum, you're using mathematical reasoning to model gravitational dynamics. Your brain, roughly 3 pounds of organised matter, about 10 to the 20, 8 atoms, mostly water with some proteins and lipids and electrical activity, can model objects millions of times more massive than planets, can comprehend processes lasting incomprehensibly longer than human lifetimes, can grasp phenomena no human will ever directly observe. This capacity is extraordinary, beyond measure. Consider your own existence in this light. You are approximately 10 to the 28 atoms, mostly carbon, hydrogen, oxygen, and nitrogen, elements forged in stars that exploded billions of years ago. These atoms, following quantum mechanics and chemistry, organize into cells, cells into tissues, tissues into organs, organs into a body with a brain capable of abstract thought, of mathematical reasoning, of scientific inquiry. That brain can understand black holes existing billions of light years away, evaporating over timescales, exceeding the universe's age by factors of 10 to the 57. The atoms in your head comprehend phenomena infinitely beyond their individual scale. Quantum fluctuations in neural synapses process information about quantum processes at event horizons. Electrical signals in neurons model space-time curvature. Biological matter contemplates the most extreme non-biological objects in existence. This is remarkable beyond measure. Now, we must avoid false humility. The tired refrain, we're insignificant specks in a vast universe. This is incomplete. We are cosmically small. Yes, our planet is tiny, our sun ordinary, our galaxy one among billions. The universe is incomprehensibly vast in space and time. But we can understand the cosmically large. We can comprehend black holes and quantum mechanics and relativity and evolution and chemistry and the origin of elements. This is significant. Size isn't the only measure of importance. Understanding is an achievement. Consciousness is remarkable. The capacity to uncover nature's mathematical structure through reason is extraordinary. We are the universe's method of understanding itself, and that matters. Some might argue science explains away wonder, that understanding diminishes mystery. The opposite is true. Black holes are more extraordinary, knowing they evaporate, than imagining their simple, eternal prisons. Quantum vacuum fluctuations are more fascinating than empty space actually being empty. The holographic principle is more profound than straightforward three-dimensional space. Understanding deepens wonder rather than eliminating it. We treat human understanding as separate from natural processes, but it isn't. Understanding is something the universe does through sufficiently organized matter. Intelligence, consciousness, scientific inquiry. These are natural phenomena emerging from complex arrangements of atoms following physical laws. We are how the cosmos knows itself. This isn't mysticism. This is observation. We began with a simple misconception. Nothing escapes black holes. We end with transformed understanding. Black holes are temporary, radiating, thermodynamically integrated structures that preserve information while slowly disappearing through quantum processes at their event horizons. The universe maintains consistency. Quantum mechanics and general relativity both apply. Both matter. Both work together at black hole horizons through subtle mechanisms we're still fully understanding. Thermodynamics extends from coffee cooling to black hole evaporation. Information theory connects computer science to cosmic questions about event horizon physics. The mathematical framework describing ice melting also describes the most extreme objects in existence. Nature refuses to create permanent exceptions to its own laws, and we can comprehend this. Primates on an ordinary planet, studying nature through careful observation and mathematical reasoning, have determined what happens to black holes over timescales exceeding the universe's age, have understood temperature and entropy for objects defined by preventing escape, have grasped quantum processes in curved spacetime despite having no direct experience of either quantum mechanics or significant gravitational fields. Both facts inspire wonder, what black holes do, and that we can understand what they do. The misconception has been corrected. The understanding has been built layer by layer, from classical predictions through quantum corrections to thermodynamic integration to cosmic implications. The wonder has been earned through intellectual effort. The journey has transformed not just knowledge, but perspective. Black holes aren't cosmic villains or eternal prisons. They're sophisticated thermodynamic objects fully participating in the universe's evolution, revealing deep connections between quantum mechanics, gravity, information, and space-time structure. They're temporary structures in a fundamentally transient cosmos. They're windows into how nature maintains consistency even in the most extreme circumstances. And we, arranged matter contemplating arranged matter's behavior, can understand them. The universe is under no obligation to make sense to us, yet it does. The most incomprehensible thing about the universe, as physicists have noted, is that it is comprehensible, that black holes follow mathematical laws we can discover, that quantum mechanics and gravity work together rather than contradicting each other fatally, that nature maintains internal consistency across scales from the Planck length to cosmic horizons. We are just an advanced breed of monkeys on a minor planet of a very average star, but we can understand the universe. That makes us something very special. The atoms in your body, forged in stars, assembled by chance and chemistry, organized by evolution into neural networks capable of contemplating black holes, have just journeyed through one of nature's most profound lessons. Nothing is permanent. Everything transforms. The universe preserves information whilst radiating entropy. Quantum mechanics defeats even extreme gravitational confinement, and conscious beings can uncover these truths through mathematics and reason. Look up at the stars. Somewhere out there, black holes are slowly evaporating, radiating quantum particles into the void, participating in the universe's long journey toward maximum entropy. They're not eternal. They're not mysterious exceptions. They're dynamic thermodynamic objects we can understand. And that we understand them at all remains the most remarkable fact of all.